we are going to solve a very interesting lead code problem, that is maximum total importance of road. In this problem, we have been given a graph consisting of all the nodes, where each node denotes the cities and the edges between those nodes denotes the roads that are connected. So let's understand the problem first. In this problem, these cities are connected by some bidirectional path or edges. Now every city has been assigned some rank, right? 4, 5, 1, 3, 2. Now this rank will vary from 1 to 1, 1 to n, where n denotes the number of cities. So for example, if the n is 5, so the rank can vary from 1 to 5. So let's, for example, let's take a test case. We have a city 1, we have a city 0, we have a city 2, we have a city 4, and we have a city 3, right? So let's assign, so we know the rank can vary from 1 to n, right? 1 to n, that is for this test case the n value is 5, so rank can vary from 1 to 5, right? So now let's assign some random ranks. Let's say for this city 1 we assign some rank 1, city 3 we need we give 3, for the city 0 we give no, I cannot give 1, kind of rank 1 has already been given. We cannot give 0 because 0 is not portable. The rank must vary from 1 to 5. So let's assign rank 2 for this one, and for 2 we give rank 4, and for rank for this 4 we assign rank 5, right? So let's calculate the importance of the road. Now you might say, what is the importance of road? Now the importance of a road between a city is a summation of values of these two cities. Let's say for the road that goes from 0 to 1 and 1 to 0, the importance of this road is 2 plus 4, 2 plus 4, that is 6. Importance of this road 1 to 2 is 4 plus 5, that is 9. So for this graph that we have uh, considered, let's calculate the importance of this road. Let's say from 0 to 1 there is an edge or path, from 1 to 2 there is a path, from 0 to 2 there is a path, from 1 to 3 there is a path, from 2 to 3 there is a path, from 2 to 4 there is a path, right? So let's calculate the from road importance of road from 0 to 1, that is 0 to 1, that is 1 plus 2, sorry, 1 plus 2, that is 3. From 0 to 2, sorry, from 0 to 2, from 0 to 2 there is a road, and it is importance of 2 plus 4, that is 6. From 1 to 2 there is a road, and it is of importance 1 plus 4 of 5, right? From 1 to 2 3, 1 to 3 there is a road, that is 1 plus 3, that is 4. From 2 to 3 there is a road, that is 4 plus 3, that is 7. And from 2 to 4 there is a road, that is 4 plus 5, that is 9. So the summation of all the rows we need to calculate. So that is 3 plus 6, that is 9, plus 5 14, plus 4 that is 18, plus 7 25, plus 9 that is 34. So this is the cost for this graph. Now is there any other combination possible for this one? So let's say for this one, let's consider this one. Let's say I assign rank 4 to the city 1, assign rank 3 for this 3, assign rank 2 for this 0, assign rank 5 to this 2, and assign rank 1 for the city 4. Now let's calculate the total importance. Now from 0 to 1 it will be 4 plus 1, 5. From 0 to 2 it will be 2 plus 5, that is 7. From 1 to 2, that is 1 to 2, that is, yeah, this one, 4 plus 5 9. From 9, yeah, cool. From 1 to 3, that is this one, 4 plus 3 7. From 2 to 3, that is 2 2 3 2 2 3, this one 5 plus 3 8, and from 2 to 4, this, no, sorry, this one 2 to 4, that is 5 plus 1 6. So let's calculate the total importance. If you calculate the total, it is 5 plus 7 12 plus 9, 12 plus 9 is 21, plus 7 28, plus 8, that is 36, plus 6, that is 42. It shouldn't be 42, I did something wrong. Let's say 5 7 9 7 8 6 5 7. I think I did something wrong, because from 0 to 1, that is 0 to 1, sorry, 0 to 1, it is 4 plus 2, sorry, it will be 6, yeah, it is 43. So this combination is the highest possible. For this type of rank, the importance of the road can be maximized. So this is what the problem statement is. So uh, what comes to your mind when you finish this problem? For example, if you have watched it very carefully, some nodes, if you might see some nodes have higher connectivity than other nodes. For example, this node 2 is connected to four other nodes. For example, 1 is connected to 2, 0 2 is connected to 2, 3 is connected to 2, and 4 is connected to 2, right? So this node has a maximum connectivity, and this node participates in most of the combination. For example, this node has a value 5. So if you look carefully in the result, in my result, this 5 has participated in most of the calculations. So it has a higher participation. So this value will be of higher importance in my resultant number, right? In my result. So don't you think that if I calculate, or if I track all the higher degree node, and if we assign highest rank to those higher degree nodes, we can arrive at the solution. For example, this node has a degree 4, which is of the highest degree in the graph. If we assign the highest rank, that is 5. Now, if we assign highest rank 5, the this node will yield the maximum result for me. Now, this node has a degree 3, which is the second highest. Now, if we assign second highest rank, that is 4, to this node, it will yield maximum result for me, and the same goes for other things. So my I will do one thing, I will calculate all the degrees of the node for for this graph, and just sort this the entire list in the descending order of the degrees, and try to assign the ranks as per their degrees, right, as per the descending order of degrees, and try to calculate the result. So it's a bit easy solution if you have understood what I've said. So let's code this thing up. It's, to be honest, it's not that a very complex graph problem. Generally graphs are very daunting. So let's calculate the number of edges, that is rows dot length. Now let's let's traverse this entire graph and calculate the degrees. Let's say u, for example, we have a connection between u and v. So u is a city, right, and v is another city that is connected, right? For to calculate the in degree, we need an array, right? Let's now, whenever we for this age 0 and 1, when you calculate the degree, now this 0 is connected to 1 and 1 is connected to 0, vice versa. So whenever we calculate in degree, this will also be calculated, and it will also be counted. So let's count for both of them. I will increase the degree for both, right? So this is it. I have the degree for all. Now I need to have some pair. I need to have a pair of, let's say, node, I need a node, I need a degree, and I need to assign some value, right? Now you will sooner understand why I'm doing this. Mhm. So I am done with it. So let's use this thing. So have a array list of this triplet type. I need to store this, right? Because unless we store in something, we cannot sort this thing. So let's store this. Now let's go through this in degree array. Or let's, yeah, cool. Because I have calculated the degrees of all the nodes. I need to have the maximum degree sorted by at the top of the array list. So I need to sort them in order of the degrees. So let's, here I denotes the node. Now the in degree will denote the degree of that particular node I, and rank, let's say rank, for example, let's say we do not assign any values for now. Let's not assign any values for now, so let's keep it as 0. Now I have computed the array list. Now I need to sort it. This is very important. Let's sort this list by ascending order of degrees. So let's sort this thing, b dot degree. Let's not do any mistake. I do a lot of typo. Dot degree, yeah. So the template, this list has been sorted in descending order of the degrees. So the highest degree node will be at the top, or it will be at the will be at the front of the array list. So the rank, now we know if there are n cities, our rank can vary from 1 to n, right? And we will assign the highest rank to the highest connected node, right? That is 2. Now at the front of this array list, we already have this highest node. So let's initialize my rank as n. Now let's traverse through this array list. It is temp.size I plus plus. Now I need to assign the rank. Let's say it's value, not rank, because this is the value. This is the value pool. Now assign the rank. I assign the highest rank to this highest degree node. Now please don't forget to minimize this, because I have assigned the rank 5 to this node, and the second node is 1. So 5 minus 1, I need to decrease this by 1. So 4 will be assigned to the second highest degree node. So this is how the things work under the hood. So now I have everything calculated. I need to calculate the result. So before calculating the result, I need to hash them all, right? Because if I don't hash it, I won't get the node. Now now the graph starts from 0, 1, 2. This is how I will scan the graph. But there isn't any guarantee that the 0 node will be of highest degree, because the highest degree node will be of 2, right? So if we scan this temporary list, the first node that we will get is this node, right? So it will be very problematic for me to calculate the result. So let's hash them all. It will be very easy for me to calculate. You will also understand why I'm doing so. Just code this thing right now. Now I have do it. Now let's go through this temporary list. Now hash them. Now for hash, I need the node index, that is node, because the index will be the because the hash will be, the key will be the node, and the value will be the triplet, right? Triplet object. So to do so, the node is um, temp dot get I dot node. this is the node, and this will be the team dot get I, because this is what I want to do, right? Because the key will be the node and the value will be the object, triplet object. You will also understand very soon why I'm doing this. So no need to worry. Let's set long race. Now let's go through this array. Go through this graph. This is like this one, what you were doing earlier. This is the graph. This is even v. Now for this zero, I need to know what is the rank and what is the rank of this node. So how to do it? We already have a hash. We hashed all. So hash of u is the node. Now this key is the node, right? So u is the node. Hash dot u will give me the node, and now I need to get the rank, right? So rank will be dot value. Very simple. So do the same thing for this one. This is actually very intuitive, not much to be explained. Just code this thing by your own hand, and you will know what I'm doing. Just calculate the summation of all. Now I have done everything. Now I'll just return it. I did some problem again. Yeah, the test case passed. Yeah, it passed also. And the time complexity for this approach will be for sorting this collection, we need a order of n log n, where n is the number of cities or number of nodes. Now this is the most expensive operation in this algorithm, and rest are all linear. Almost you can see see my code, the rest are linear. And this approach was a bit expensive in terms of space complexity, because we used a lot of space for calculating the degrees. We used in degrees array. We had a list of objects. We had we had used some hash maps to store the to get a node and object key value as a key value pair. So it was a bit. So let's understand this thing. Time complexity will be order of n log n, where n is the number of cities, n is the number of cities, and space complexity will also be of order of n. Let's say we are pushing every cities into our array list or collections, whatever we have used. So it will be order of n as well, where n is the number of cities. So that's it from me. It was a not that difficult graph problem, to be honest. It was a very easy problem comparing to other graph ones. So it was that's it from me. Thank you.